Good evening and welcome to the Doherty Institute and to this Convergence Science Network presentation. My name's Luan Ismail, I'm the Executive Director of the network, and it's a great pleasure to see so many of you here this evening. Our speaker, a graduate in mechanical engineering from Germany, has come to Melbourne recently to take up an appointment as the co-director of the Monash Institute of Medical Engineering. And Professor Steinseifer also continues to have an appointment back in his alma mater in Aachen, in Germany. And he's also a consultant for the Victorian Heart Hospital, and his role there is to help design a facility where the research and the clinicians are in close contact, and hopefully that will deliver improved health outcomes. I guess what that slide doesn't tell you is that he's really a world leader in this field. So without further ado, please give a warm welcome to Professor Steinseifer. Thank you.
Okay. Yeah, also from my side, a very nice welcome, and I'm very happy that so many people are here to join this presentation, and Luan has already introduced me, so thank you very much for that. Tonight, or this evening, I would like to talk about heart matters, technologies for treating the failing heart. I was thinking about, it's a little bit more a scientific title, I was thinking about also just calling it broken heart, but I thought that then maybe we would have some mix-up and people think that this is the comedy festival. So finally I decided to take a little bit more a serious title, because what we're talking about when we talk about broken hearts, it's nothing really funny, because it's even deadly serious what we're talking about. We're talking about the real heart and how we can treat any diseases that the real heart has. Now, saying that, I have to start with something that is not very fortunate also, and that is that 1 out of 3 Australians die of CVD. I know Australians like abbreviations, so I took it CVD. Cardiovascular diseases. Cardiovascular diseases are everything that has to do with the heart. The cardiovascular is the vessels, so that means everything that has to do with the heart and the vessels. Vessels means also strokes, etc. They are all included in these cardiovascular diseases, and but it's not only in Australia that this is a problem. It's also anywhere else in the world it's a problem, and particularly also will be a bigger problem. It's one of the diseases that has the highest rise also in the next 20-30 years. And as you see here, by 2030 we'll have about 1/3 almost of the population dying from cardiovascular diseases. So it's really something that's coming up and that we have to look at. And even if we look at the region here, Asia-Pacific region, you see the number of people older than 60 years of age is expected to double by 2025 and triple by 2050. The proportion is likely to increase more in the Asia-Pacific region, and that's where we are here. Half of the world's cardiovascular burden is predicted to occur in this area. So you could see it from both sides. It's something dramatic. On the other side, it's a big market, so something that people are looking at. And what is the problem here? Because for the cardiovascular diseases, probably you are all aware of that. We have overweight, hypertension, we don't move too much, etc. And if we talk about the Asian region, actually cardiovascular disease, for example, in China, we're not very popular. It's quite okay. But also there, the whole nutrition changes, so it's not so much salads anymore, it's fatty, greasy things that, or food. So that also leads to that we have more of these cases in the Asia-Pacific region, and also we see that in Indonesia and other regions, and that's basically almost half of the world's population that's living there, and there is a big problem. Now what happens? We have then coronary artery disease, we have strokes, cardiomyopathies, that is just an illness of the heart muscle. We have valvular diseases, that means the heart valves can be affected, etc., etc. So there are many things that can happen to the heart, and so that's a major problem. So if we want to talk about how to treat the heart, I think it's first of all important to understand what the heart does. So I'm very sure, if I look around, I'm very sure that everyone in this room has a heart. I'm very much hoping that all these hearts are beating for the next 45 minutes. So, but I'm not so sure whether everybody knows what an incredible achievement the heart does, what it does in our lifetime. And so I would like to go into that a little bit. You probably know that the heart has two chambers. It has a left and a right chamber. And basically, it's even the other way around. You have to see it from this side, left and right. So the left chamber is, or both chambers have heart valves. And it's a hollow muscle. That means it can expand. And with that, it gets filled with blood. And then it can eject the blood by a contraction, like a muscle does. So we call that also the systole is the extraction phase. And we have the diastole is the phase where the heart muscle gets filled. And what is important, if we look at it, we have basically everything is one circuit, of course. We are in one body. But we divide between the pulmonary circuit, that's the circuit where the blood is pushed through the lungs just to get the O2, means the oxygen, and then also to get the CO2 out. And then it goes to the left heart, and the left heart is the one that pushes it all around the body. That means we have two different situations. That's very important to understand. Because we have in this right heart, as we call it, for the pulmonary circuit, we only need a little pressure. The lungs are don't have very big resistance. That means we don't need very much pressure to push the blood through there. But if the heart needs to push it to the toes, to the tips of the head, to the fingertips and everywhere, through the organs, that means for that it needs a lot of power. And that is then in the left circuit we have pressures that are more than 100 millimeter mercury. You see that also here. These are pressure curves, and when you go to the doctor, or GP as you say here, when you go to the GP, he will say, oh, everything's fine, you have 120 to 80 or 130 to 80. That means it's in millimeter mercury. Clinicians still use very old-fashioned units. They do everything millimeter mercury as pressure. So that means it's basically the pressure that we need in order to get really the blood in all the corners of our circulatory system. So let's look at some other data of the heart. I have just taken two absolutely normal standard people. I have told Alexa at home, please, Alexa, give me two people off the internet, just the most normal people that you find. And this is, I don't know who it is, so it gave me these two people, a woman and a man. So just normal standard people. And what we have there is that we have the weight of the heart and the volume of the heart. And you see, there is always a saying that the women have the greater heart. That's not true. As you see here, men have the greater heart, and it's also a little bit more heavy. So this is one of the things that we have to put straight. So when you're sitting there, you're in rest. Usually you have then a cardiac output, as we call it. That means about 5 liters of blood are pumped around in your body in a minute. Okay? You know that the heart is working pulsatile. You have a pulse. That means it's done with several strokes. And we have this heart rate is in the range of 60, 70, 80 beats per minute. Also, again, for a man, a little less because he has a higher stroke volume because the heart is bigger. So this is what usually happens while you're sitting here. You're not doing anything. That means you're in rest. I hope many of you do a lot of sports. And when you do that, your heart can really go up. It can go up to even up 20 liters per minute. That means when you go running, when you do some sports, in a normal person, you go up to 20 liters per minute. So that's quite a lot. That's 2 buckets full of blood in 1 minute. So if we put that a little further, there are extreme people. And one of those are bicycle riders. They are very extreme in there. Does anybody know who that is? Come on. This is Australia. This is a hero of Australia, isn't it? Cadel Evans, of course. This is the winner of the Tour de France, I think in 2011 or something like that. So he, for example, or the bicycle riders in general, they have hearts that are 1.6 liters. They are real big hearts. And so what they can do is that they can throw out 170 milliliters per stroke. And that means that they only need 30 strokes to get this 5 liters through the body when they are in rest. So they sometimes go to the GP. GP measures the pulse and says, you're deadly ill, because he thinks he doesn't have a pulse. But indeed, they go down to maybe in the range of 30 beats per minute. So in his case, also when he goes up maybe a mountain in the Alps or somewhere, it can go up to 40 liters per minute, his cardiac output. And so I calculated it roughly when you are sitting here in 45 minutes. We have a little longer today because of technical issues, but usually in 45 minutes you would have 225 liters. If he would go full power for 45 minutes, would be 1,800 liters blood that his heart pumps. So that's dramatic. A bathtub is about 200 liters, so you make a bathtub, he makes, I cannot calculate that so quickly, but probably something in the range of 8. So that means it's a tremendous achievement. Also, if we look at the durability of the heart. So this is, by the way, I checked that also in Australia. You're very lucky. In Australia, the average life expectancy is 82.45 years. That means it's one of the highest life expectancies in the world. That's also very interesting. And so that would be 722 hours, 1,000 hours, and it would be 3 billion cycles that the heart does in a lifetime. So if we compare that, this is an engine. This is, in this case, I don't know whether it's a German car, probably. But we would, as engineers, say if we calculate the lifetime of an engine, if it makes 1 billion cycles, that's already good. So the heart makes 3 times that. So the heart is really tremendous in that regard. And the final thing, also what the pump volume, if you calculate that all, 40 million cycles a year, and then you have all these 70 beats and 70 milliliters per minute and all this, sum it up to the lifetime, it's about 215 million liters. If you, to get an idea from that, it's very hard to get an idea from that, but this is the highest building in Melbourne, this Eureka Tower. Roughly calculated, it has about almost 400 milliliters of volume. That means it just needs 2 hearts from a lifetime. 2 hearts are not much bigger than a fist, and these little pumps, 2 of those would fill the whole building within a lifetime. So it's really something, I think it's always, I like to bring this data because it's, you have to have respect of the organs and the body and what they are doing in order to really be able to help if there is something wrong. So what do we have if we have a problem now? Because 80 years and all this, that means that there can be some problems. First thing is always lifestyle, prevent. That means that you try to prevent that you get any problem. I don't have to explain that in Melbourne because Melbourne is a sports town. You do a lot of sports, you're running out there, so that's fine. Just eat some salads. There's also some healthy food, then it's all good. Drug therapy is the next step. That means if there are some problems, the next thing would be, for example, if you have hypertension, that you get some drugs in order to bring down the blood pressure. As an example, if this doesn't work, in the next step, it would be surgical, some kind of intervention whatsoever. You try to repair something, that would be the next step. And then, last but not least, if nothing works out, then you would have the implants. And I would like to talk about these implants a little bit, show you some of these implants and what it means to make them. With regard to the time, I cannot go through all of them. So these are stents, heart valves. It goes to pumps that support the heart and even up to a total artificial heart that replaces the heart. I would like to, with respect to the time, just go to the latter ones, means just to these pumps that support or replace the heart. Now what's the problem here? That we call that, when we have a pump that supports our mechanical circulatory support, because there's a mechanical pump that helps the circulatory system. We have a chronic heart failure as an example, and there's a definition for that. There's 4 steps that you can have, and that is depending on how much you're limited in your mobility, etc. And of course, the worst one is if you have a stage 4, NYA, as we say in short form, New York Heart Association, it's a definition, that you're unable to carry out any physical activity without any problems. That means those patients are basically lying. They cannot do anything anymore. They are lying in the hospital and they cannot move because they're immediately out of breath. So what happens then? Gold standard, heart transplant. Best thing you can do still, clearly, to make that very clear, heart transplant is the gold standard. We have a major problem there, that we have about 150,000. Much more than that, this is even conservative approach. If you say we only take the patients that are really still healthy other than the heart, and you only gave them a heart, you have about 150,000 in the world, Western world, I have to say, where it's registered. So, but if you look at it, we just have in the range of 4,000 heart transplants. Why? Because we don't have donor organs. That's the problem. We have a big problem there, and that means there is no alternative for these people, only for a few of them. So we have a massive lack of donor organs, and so the mechanical circulatory support is then an option for these people to survive and to live on. Now, how does it look like, a mechanical circulatory support, a pump like that? You see here the body, you see the heart. This is the tip of the left heart, and again, high pressure area, left heart. That means if most of the time the left heart is of course affected, and if the left heart is affected, it's also worse than the right heart. So that means it's a big problem. You see the pump is attached to the heart, and then it pumps into the aorta, into the main vessel. That means the heart, this pump is parallel to the heart and helps the heart to pump whatever is needed in the body. So if you look at it, we had types. We had the first generation pulsatile blood pumps, because in the 80s we thought our heart has a pulse, we need a pulsatile pump, of course, because the body needs pulse. So these pumps were made, and what happens is these pumps have a pulsatile flow, but they are bulky. They need external drives and all this. I have one of these pumps here. This is a typical pump that was done in that time. A pulsatile pump has a membrane, and you push with the air, you push the membrane back and forth, and with that you can pump the heart. We can put it up there for later if somebody wants to look. Problem is big on one hand, and what you don't see, there must be a drive system. That means a compressor that pushes the air also into there. That means it's not only this, it's a big thing. You cannot implant that. So that means that was a disadvantage. And then we came to the year roughly 2000, around this time. The so-called continuous flow pumps came up. That means little pumps that have a rotor in there, as you see there. Now, if it opens, they have a rotor in there, and they push the blood through there. Much smaller, but they have one thing, of course. They don't have a pulse. So they are continuous flow pumps. Question, wake up question. Do we need a pulse? Who thinks we need a pulse? If we have clinicians here from cardiovascular, they shouldn't vote because they know. Who thinks we need a pulse? Nobody. 1, 2, 3. Who thinks we don't need a pulse? So, who abstains? That must be the other ones. Please up. I abstain. So, but let's get to that question a little later. So, we have continuous flow pumps. They are small. They only need external batteries and the control. Like here, like you see here, they need a battery, something, that's it. So, it's very easy. So, these pumps, we have also, I go back because it says here second and third generation. We had at times that these pumps were, you see here, there's the rotor in there, you see some red points. These red points are the bearing system, and the blood is going through there. We call it a blood immersed bearing. That means the bearing system is in the pump. We had to keep the rotor somehow to rotate. But that has a disadvantage because wherever you have a bearing, you have wear, and these pumps have to run a long time. Think about life expectancy, and we have blood damage because the red blood cells get in there and they get squeezed and they get damaged. So what we do nowadays also, that we have fully suspended rotors, that we have, for example, with magnetic forces, we keep the rotor in balance all the time. You know that also when you drive from Shanghai to the airport, there's the magnetically levitated train, and this is in principle a similar system. So we have no wear, and we have a low blood damage there. So that's an advantage. That's a progress that was made. And if you look at that, you see this is the probability of survival after a certain time, after 24 months. And you see that the continuous flow pumps in the patients show that the patients survive longer and better, so they clearly have an advantage. And I can tell you nowadays, these pumps are not implanted, and the pulsatile pumps are not implanted de facto anymore because it's fully taken over by the continuous flow pumps. As it says there, continuous flow pumps show better results. Now, give you an example how it could look like. You have seen one of the pumps before. That's a little bigger one, and it's a little further away from the heart. The heart is in a cavity. Below that is the diaphragm. That means in this case, the pump, this pump is even below the diaphragm. It's even in the abdomen. Whereas if the pump gets smaller, you can put it closer to the heart. You can more or less plug it into the heart. So it's much closer, and you have enough space in the cavity to plug it into there. And that's then a better possibility to even implant it, as we call it, minimal invasively. So There are a lot of success stories, as you see here, people that run around, even younger people that are hiking in Australia, not in Australia, in Austria, because you don't have so many mountains here, so that was in Austria. So even you see young people can be affected. It's not only something for, it's mostly old people, but even young people. This is probably the most prominent one. Does anybody know who that is? Dick Cheney, the vice president, former vice president from the United States. He had a pump like that. So you see the patient are basically doing pretty good. Don't forget, these were class 4 patients, patients that were dying. They wouldn't be there if they didn't have this pump. So that means that is pretty good. And you see, if you would give the patients only medicamentation, this is this curve, after 5 years, they would more or less be all dead. There is no chance. If you get this, but this is heart transplant. If you give them a heart transplant, they are about almost 80% after 5 years are still alive. And if you look after 2 years, they are even 85% are still alive. This is a heart transplant. This is the gold standard. But now let's look at our pumps. If we have the newer types, like these ones as you see there, we see after 2 years a 86% survival. That means we have a survival that's basically comparable to a heart transplant. That means we have reached maybe a real alternative for people that have a broken heart. So then if you even, survival is one thing, but quality of life is another thing. We also have to look at that. And these people, if you look at there's this EQ 5D visual analog scale. This just means it's a questionnaire where you ask the people, do you feel good, and this and that, and then it's evaluated, and then you get a score from 0 to 100. 100 is good, 0 is not good. So that means at the beginning they don't feel good. If they get the pump, they feel much better. So that means there is a clear improvement in that. And you also see that if you look at the patients, this is where the red ones are with severe problems. With blue is they only have some problems, some residual problems. And you clearly see that they also say they have much less problems when they do something. So clearly also a quality of life improvement, not only survival. Well, like in medicine, there's also a but. So sounds fine, sounds wonderful, but we are by far not there yet to say this is a treatment that we can really apply on a very large scale. And so because the people get infections, they get clotting, bleeding, that means they have clots in the pumps or someplace else, or they get strokes, they have pump cable, simple things like pump cable damage, battery failure, and then mismanagement by caregiver and dementia and device handling. They have a little controller, and those are sometimes old people, and we get to that later. There's a question of usability. If you have some buttons there and you press the wrong button, then you have a problem. And this is a life-saving device. So it's something that's very, very important. We'll get to that a little later. If you look at it, and this is really always, I think it's always dramatic to show that 2001, that what you see there, was all implanted. That's not outside the body. That was the first time that they tried to make a fully implantable pump with I showed this one that has needs a generator for air pressure. And these have an own motor integrated. That means it's fully implanted. Everything like that needs to go in. And if you look about 6 years later, this is the same thing, does the same thing. This is a pump that you can implant, does the same thing. Just continuous. And I put that proudly always on there. We developed this pump in Aachen, and it was also on the market. And it's currently revised and will come back again. So, and this is how it looks like. You have to, I have a X-ray picture of the patient, and I thought that I don't do that to you. So we took an animation how it looks like. So it's all implanted, and so this is basically, if you look at this Circulatory pump, you can place it even like almost like a pacemaker. You place it in a little pocket, and then you can make a cannulation to the heart, and then you pump back from the heart. You take the blood from the heart and pump it into the subclavian artery. Subclavian artery is the one that goes to the arm. Now you would think, what is that? Because he would probably stand there and the arm would go up because all the blood goes in the arm. It's amazing what the body can do in terms of autoregulation. That means the body regulates that. The vessels can widen, contract, everything, and they distribute it correctly. So it works. At the beginning, everybody says, it doesn't work, but it works. So The pumps, if you look at the trend, the pumps get smaller and smaller and smaller, of course. Then you can go even more minimal invasively. If you look at this cannula that was plugged in the heart from this pump that you have already seen before here, and you look at nowadays a pump, that means the pump even has the same diameter, and the entire pump is in there. That means you have, in the meantime, in a diameter like that, you have an entire pump. I would go even one smaller. This is the smallest pump in the world. This has a 12 French pump motor. 12 French is divided by 3, 4 millimeter diameter. And it's inserted through the femoral artery. That means you shift it with a catheter into the heart. You don't even have to do surgery anymore. You get the blood out of the heart and you pump it into, you see there's a rotor in there. The rotor does 50,000 RPM, roughly, and that over certified 7 days minimum. 7 days minimum. If you have the race cars, the Ferrari driving around with 50,000 RPM for 7 days, the motor would be broken. This one still runs for that time, and we also developed that. It's actually on the market, and if there were cardiologists here in the room, they all know it because it's a pump that is used in the clinic very often, more and more. It's just a little expensive, but other than that, it's good. So what happens now if we have certain situations where we cannot use these pumps? As an example, we have a thrombus, a blood clot in the ventricle, in the heart. If we attach a pump and switch on the pump would pump this blood clot through the body. We would get strokes and all kinds of things. You may never do that. This is very dangerous. That means these are things where you cannot use a pump. Or if you have, for example, a septal defect, you have in the wall between the two chambers, you have a hole. If you then start to work with a pump, you would draw the blood from the other side and you would have a total screw up. You may not do that. So that means these are indications when you may not use a pump like that. And this is then the only option then, other than, of course, the heart transplant, again, is then really what we call a total artificial heart. Total artificial heart means it was a long time, it was a dream, question mark. And so this was in 2001, there was a new one coming out, but it's not a dream, it's actually something that is existing. Even you look at the time scale, you see in 1969, there were two people, Denton Cooley, a famous surgeon who just recently died from the United States, from Houston, Texas, and an engineer, Domingo Liotta. They made a total artificial heart, and they implanted it for the first time in a patient. They had a patient, they didn't know what to do, no donor heart, nothing, and they said, they had it in the lab, they said, let's try. At that time you could do that, today it would be a different story with regulations and all this, but at that time when the surgeon says, I do that, he does that. And so they put it in, the patient survived for about, I think, 80 hours or something, wonderful. A donor heart came, and then they quickly put in the donor heart because they were afraid, and the patient died with a donor heart. Why is that? 1969, the first heart transplant ever was on the 3rd of December 1967. That means it was just a little 1.5 years after the first heart transplant, and all these immune system things were not so advanced like they are today. So that means the patients very often had immune reactions and then they died from that still. It was at the beginning of heart transplant. So then the first one that was put in for a longer time, 1982, Jarvik 7 it was called, that was in Salt Lake City, Utah. That was already in the patient for more than 100 days. Maybe there are some people in here, maybe they heard it at that time. Barney Clark was the name of this patient. For me, it's always an interesting story because I was actually as a student, as an internship in Salt Lake City, Utah when that was implanted, but I left in October and they put it in December, so I missed it for a few weeks. So this is nowadays the Syncardia total artificial heart, and then afterwards there came another one, the AbioCor. I will show you them a little bit. That was in 1993 when they got approval to put it in. That basically means this Syncardia total artificial heart is a replacement of the heart. You take the heart out and you put an artificial heart in. And this is how it looks like. Looks pretty good. And we have about 1,700 implants since 1993. And it's getting a little more and more, about 100, 120 per year worldwide, I have to say. So it's not a standard, but it's done. There are patients living at the moment with total artificial hearts on this planet, several. So if you look at it, there is a patient with a total artificial heart. She's even there, she's younger, she's in the gym and looks fine, she's laughing. She was dying before. So that means it looks quite good. And you would say, what's the problem? But if you look a little closer, at the end of the movie, you see that there's always something next to her, this thing, that you might have seen, and she could never get rid of that because that was the drive system. That was the thing that produced the compressed air. So that means she always had to run around with this thing. This was old. That was in the maybe 90s, end of 90s. Got better and better. Then after a while, they make them smaller and smaller. And nowadays you even have the freedom driver that you even can put in a backpack, or you have it like that, like a bag, and you can run around and the patients can go out and they're much more mobile, which is very good. There is a disadvantage, what you don't see on the pictures, you could only hear. If we had a patient in this room that had a driver like that, we would have trouble to listen because it would go all the time. These patients are often isolated because nobody can talk to them. It's difficult to talk to them. They themselves don't have a problem with it, but most of the time the people are next to them. So it's a tough thing. So that's why the people thought about it and say we have to make a totally implantable total artificial heart. That means we have to bring it in the body completely. And this is like this. It already has a drive system in there. This is this AbioCore total artificial heart. It came in 2001. It was first time implanted. And it had some implanted controllers, a battery implanted, and it had a so-called TET system. That was a system where you transmit the energy without a cable. We get to that a little later. So this is then the patient sitting in TV, and he could talk normally because you wouldn't hear anything, right? That was then much easier for the patient. If we look a little further, and now we go back to our question, our poll. Do you say poll that we had at the beginning, pulsatile, non-pulsatile? In 2011, there was the first time that people did something else. They put 2 rotary pumps, these pumps that you have seen before. They took the heart out and put 2 of these pumps in there. That means they had a patient then that was again in Houston. Houston is very famous for things like that. They had no heartbeat at all in this patient. This patient unfortunately died 4 weeks later from other things, not related to the pumps. So the final answer, if it works without pulse or not, is not yet given. And when I say you only support the heart with 1 pump, the patients still have a residual pulse because the heart itself is still pumping and it pumps the blood into the pump, and so some pulse waves go through the pump to some degree. It's a lower pulse rate, it's not such a high amplitude, but it's still some pulse that's there. So there are some other developments on the world, 4 major ones for total artificial hearts. So there's still something ongoing. In France, one, the Carmat, that has been implanted in 4 patients now, not so successful. Then the Reinhardt. The Reinhardt is one that we developed at my other institute in Germany. So we also do a total artificial heart. That one is the best one that's currently under development by far. And so there's also 2 very interesting ones, the Cleveland Clinic heart and the BivaCore. They are indeed now also rotary pumps. That means they will be then without a pulse, at least to some degree, without a pulse. They use the same principle without heart valves and all this like with rotors. And I want to show you that, and now I'm honest. My favorite is this one, indeed. And I'm showing that because, and you see how it works. That means it has this is just an animation. You have the left side with the red blood, and the blue blood should be the right side. And it has a rotor in there, one rotor that has 2 different blade configurations on both sides. You see bigger ones here, smaller ones in diameter there. And that's because the left heart has to pump more than the right heart. That means it's implemented that we have this difference that the left heart has to do more than the right heart. And even this rotor can go back and forth in order to balance the flow between left and right. This has another special, it's a very, very intelligent system, probably the most innovative one. This was invented in Australia. That is from Brisbane, Australia. It was developed in Brisbane, Australia with a lab that we work with also. We worked with them a long time. They were even in our lab every once in a while. And a guy named Daniel Timms. And unfortunately, they got money in the United States. That means in the meantime, it's developed in the United States. So they are not here anymore, unfortunately. It's a very, very good system. I would put my money on that. So not on ours. I can say that here now because my people are far away, so I can say. You don't tell them. So challenges. So what is, when we do all these devices, what's the problem there when we do that? We have a lot of problems. The biggest problem is always blood. Blood is very aggressive. Blood degrades polymers, it corrodes metals and all these things. So it's, blood is a very, very bad in parentheses fluid. And it clots also when it gets in contact with foreign material. Doesn't like that. It clots. We have people sitting here that are working on things like that. Also at Zyro in order to make materials where it doesn't clot anymore. It's damaged. That means if we have very high mechanical stress, we damage the red blood cells. And we have, I talked about that, we have an issue always of durability. It may never fail. And I always say that. No callbacks. It's not like, please, the last 300,000 cars come back because we have a little issue with something. This may not fail because these people are depending on that in every second. So that means that's an important point. And so implants should therefore be more or less bio-inert. There are other options, but let's keep it like that. That means they should keep their properties and they also should have that on a long term. Bio-inert also means they shouldn't change from the blood, but they should also not do things in the blood. Sometimes you have polymers where you have some diffusion out of the polymer. Like if you have polyvinyl chloride, you have the vinyl chloride that may go out of, per diffusion, go out of the polymer. And then you also have trouble because you don't want that in your body because it's toxic. So that means it should do nothing to the blood, and the blood should do nothing to the material. It should have biocompatible surfaces, no activation of blood clotting, and also not disturb the blood flow, no turbulences or stagnation, no mechanical damage of red blood cells. We can do this is a flow simulation through a heart valve. We can look at that so that we don't have circulation. I show you some examples for that. And also, of course, it should have a lifelong durability. Whatever that is, lifelong, depending on how old the patient is, but it can be 20, 30, 40 years. So what do we do? I will show you some challenges and some research studies that we do in order to investigate what's going on. Blood damage is related to the red blood cells. The red blood cells have a membrane. Inside is the hemoglobin. That's the one that can bind the oxygen. So as long as it's in there, it's fine. If the membrane has a rupture and it goes out, it doesn't work anymore. That means we have to make sure that the membrane doesn't rupture. And you see here, this is a vessel, and you see these red blood cells crashing into the wall. You can see that they can deform pretty much with their membrane without rupturing. So they can stand a lot. So what we do, we have a certain shear apparatus, doesn't matter how it works, it's just where we create high shear stresses by flow, and we can increase that shear stress. We pour blood in, and we look what comes out, if it's torn, if the red blood cells, the membrane is torn or not. And then from that, we have some kind of a result of the blood damage as a function of the shear stress and a function of the time, because the shear stress alone is not the problem. If we have a red blood cell and would just hit it, it would just deform and it's fine. If we hit it and keep the pressure after some milliseconds, then it will fail. That means it's also a matter of time. That's why sometimes in a very small pump, you don't have very much blood damage, because they have a high, like 50,000 RPM, but it goes through this pump, and then I always say, the red blood cell didn't even know that it should be damaged, so because it was so quick. So what we do from that is a so-called hemolysis model. Hemolysis is the damage of the red blood cells. An equation, it's just an empirical equation. We are engineers, we do equations. We put that into simulations, like a flow simulation of a pump. This is then a pump, and we then calculate the shear stress and everything and look whether we get problems with blood damage. And then we afterwards do some blood studies with really real blood, and if we have a prototype, and check whether everything is as we expected. Also, what can happen that we have clotting in the pumps. Clotting we look at from literature, from all the information that we have. How does clotting appear? You have the platelets in the blood. When the platelets are shared, they get activated. They have these pseudopoids. I don't know how this is named in English. With that, they get together and they form a clot in a recirculation area. What we can do now is we take our blood pumps again and we look where we have certain flow issues, and everything that's red then is a problem. That means we look at some risk factors, hot spots in the pump, and we can see here that we could get some problems, and then we could afterwards we do our blood test again, and we look at our rotor and see exactly there where predicted we have our clot. That means we have to improve something, do it better. Blood clotting on surfaces. I mentioned that before. Surfaces is also something that's very important. Many people do that they have their surfaces that they coat them with some biofunctionalization, we call that, with some, I don't know, drugs, in order so that you don't get any attachment of the platelets. What we are working in also is to structure the surfaces, because we want to see whether the platelets may like some surfaces structures more than others. So that means we implement some structures. We do that at the center. For example, we can do that here at the Center for Nanofabrication in Monash, or out in Clayton. It's not from Monash. We can then make samples, put them in a test chamber. You even learn some German here. Einlass, Auslass is inlet, outlet. So that means we have some blood flowing across. We can look under the microscope what happens, and then afterwards we see, aha. For example, if we look here, there's only one little platelet that deposited here, whereas here on this surface and on this surface there are more. So probably this surface is better. So we use this surface. So this is, then we can do this surface in our pump in order to have less problems there. Physiological interaction. We have the circulatory system, because what we do is we have our circulatory system is active. I said before that we even have our vessels can contract, and so we can autoregulate. Our heart regulates. You know that when you run up here, that the heart rate goes up. That means the heart reacts to anything. So suddenly we put to this system another system, our pump, and switch on the pump. So we'll have a reaction in the circulatory system that we have to predict. So it's not a stiff system that we have there. It's a flexible system that has an own regulation system that we cannot control. So that means we have to learn how the circulatory system works. For that, we take the organs, etc., and we make a simulation model in the computer, where we take all literature, everything that we know about physiological reaction of the body into this computer. And then we make also some so-called mock loops. These are then test stands in the lab. This is basically the circulatory system and in a technical way. And with that, it's computer driven. We can change things there. And with that, we can then go through all kinds of scenarios. That means we can look what happens if we switch on the pump, what happens if we have the cannula, different cannula, does something change? So we can do all kinds of things, scenarios that may happen afterwards. We can already test them in the lab before we put the pump on a patient. So we also have, I just mentioned this word cannula. This is where the inlet and the outlet of these systems are. If you look at the pump like that, this is the picture that you saw before. We have a cannula that goes to the ventricle, or to the heart chamber, and pumps into the aorta. Now we have this situation. If we look at this a little closer, we have basically the heartbeat coming from here, and we have the cannula in here, in the side. And so if we make a simulation, now you look at that, what happens is these two start to interfere, and we have a little chaotic situation. See, this is what happens. There is from the pump the flow coming, and this is the flow coming from the heart. And you see that on one hand we crush into that wall. If you do that for years and years, you may have an aneurysm. That means the wall gets a little, that's not very good. And also you have these three vessels, they go to the brain. These are the cerebral vessels, they go to the brain. And if you look at it, I go back one more time. If you look at it, you have flow going to the brain, but what you create here with this jet is what we call a suction pump. On the side of a jet, you have a low pressure. That means you kind of suck even from the side. And this is where, depending where the cannula is, that may be from the cerebral vessels. That means you suck blood from the brain, and that's not very good. That means what we do then, we think about how can we do new other cannulas, and how can we position these cannulas and tell the surgeon, please do them there and please not there, in order to have a better perfusion. Driveline infections. So these pumps still have drivelines because they need energy, and the energy comes through drivelines, and this is how it looks like, and they are infected very often, so that's not very good. What we would like to have is a transcutaneous energy transfer. Transcutaneous means always across the skin. Energy transfer, like you see it here, known. It's something that maybe many have at home in terms of the toothbrush, or what you also have in terms of nowadays of the mobile phones. You have a little coil on one side and the coil on the other side, and you place it there, and the energy goes from coil to coil. So easily you would do that you have one coil implanted and the other coil is outside, and then you have a transfer. Sounds good. You have no drive lines through the skin. That means you have a lower infection risks. Sounds very good. It's not so easy as with a telephone, because for two things. On one hand, before you had just the drive line going there. That was all. There's the pump implant, that is it. And suddenly, if you have this system, you also have to have much more components. You have to have some converters. You may have an internal battery, because if you take it off or if it falls off, you still have to have energy. That means there has to be a battery inside. That means you suddenly have to implant much more things. And if they break, then you have a trouble, because it's in the body, then you have to do surgery. So it's not so easy as in a telephone, where you just go to the store and say, give me a new one. So more implantable components, more energy losses. There is another thing also. You see here, that is, for example, then a battery, and this is one of these coils outside. There's one inside. We have another problem. You lay your telephone down, that's fine, but we are doing all kinds of things. We are running around, we're moving. Where do you put it? Because when these coils are not aligned, you don't have transmission. So that means you always have to keep the coils aligned, but you're moving all the time. So it's really not so easy to get good places, of course, here, because you have bones, so it's a little better than if you would put it in the belly, for example. So that means also you have to have a stable coil alignment for high efficiency. Of course, in the future, what the people are looking at is, like also with the mobile phone, same direction, that the patient's running around, and you have in the roofs everywhere you have your coils, and the mobile phones are charged, the batteries in the patient are charged, everybody is charged when he's running around. So, but this is even the people that develop things like that still say you're still far away from that. So that means this is future. But there is a lot of work on that. And it's driven more or less, of course, by the mobile phones and things. This is what it drives it. We just hook onto that and try to get something like that also. Batteries, if you think about it, when you make your system smaller, you have to have your motors, your energy, your electronics, everything needs to get smaller. Batteries need to get smaller. And when motors get smaller, the smaller they get, the less efficient they get. That means you need more battery power again. So it's always an optimization question. And so there is a lot of development that has to be put in that. Always think about it. When you go with your mobile phone, you get stuck in an elevator or something, you would say, okay, if it's going empty, okay, I have to wait until the elevator drives again, or if you're in a traffic jam or something. A patient with a pump like that has a different feeling of that. He's thinking about his life. And so that is really something that's very serious. So also less power consumption, etc. Anatomical fit, we also look, of course, that it fits into the body, particularly total artificial heart, that you have all the connectors are in the right place, etc. So you also have to look at that. So finally, and I mentioned that before, usability, very important. There's software, there's hardware, there's everything in there. It should be really easy to use, no mistakes. And also it should be appealing. The patients have to run around with that all the time, and they don't want to have an ugly bag at the side all the time. So that's little things that are also a question of usability and quality of life. That's what I wanted to say. If I tell a little story, and it's a sad story. Alarms, it says alarms. At the beginning, they had all the alarms in there, and the people, everything was an alarm. So there was a patient, it's really true, in Vienna, and the patient had an alarm. His wife, the caregiver, was trained. She knew what to do, because the patient may get a little bit in panic, and she pressed the reset button. Everything fine, the system makes a reset. What they did is, when the computer runs up, it makes an alarm to test whether the alarm works. She pushed it again. It's a very sad story. And so these are little things, and they are incredibly important, that particularly when it's also some older people, etc., that it's really usable. So easy and safe handling improves quality of life. Finally, also matter of costs. When we talk about a pump like that, we talk about 60,000, 70,000 euro. What is that? $100,000 for a pump like that. So if we look at, for example, quality adjusted life years, that's not only the years that a patient has, but with a factor in there, how much quality he had. Quality 0, quality is basically dead, and factor 1 means high quality, everything normal. And if you look at that, just to have an idea, a patient costs about 97,000 per quality life year when he gets HTX, stands for heart transplant. When he gets a heart transplant, if he gets a pump like that, it already costs 202,000. If he gets what sometimes happens, a pump first until he gets a heart transplant, we call that bridge to transplant, then we're talking about 226,000 per year. for a quality adjusted life year. That means we're talking about a lot of money. It's also something that has to be discussed. That means it's also important that we get lower cost devices. That's a big problem. In summary, cardiovascular diseases are the largest killer in the world. Deaths increase due to modern lifestyle. Blood contact, flow patterns, durability are the major challenges. You have seen that. Mechanical circulatory support is an option to heart transplant. I use the abbreviations to tease you a little bit. You're teasing me also with these abbreviations all the time. Survival rates approach heart transplant. The major trend of mechanical circulatory support is miniaturization, and total artificial hearts are reality. They work, and the best treatment for CVD, for cardiovascular disease, is prevention. With that, I'm more or less finished with that, except a little thing that I would like to give home all the time when we have something like that. You know that take-home messages. Everybody needs take-home messages. So I want to give you some take-home messages in order to avoid all that. Number one, have fun, laugh a lot. Reason, there is a scientific study. I think it was only on 300 persons, but it's a scientific study in New Orleans, where they clearly saw, with big evidence, people that laugh a lot had 40% less heart attacks. So it's important, have a lot of fun. That's one thing. And now the second thing is always, I get some trouble always when I show that. Enjoy a good glass of wine. Why is that? The point is, does anybody know what the French paradoxon is? The French paradoxon? French people drink, I think, 3 times more alcohol than Americans, for example. And they only have half the amount of heart attacks. The French people have much less heart attack, even as Germans. Also, I'm saying even as Germans because we have the same thing. At the beginning, everybody thought it must be the alcohol. So they tested the people that drank a lot of alcohol, and we, as Germans, drink more beer. That was not the point. So the French were still in an advantage. So there are some, and it's still not 100% clear, there are some ingredients in the wine that come from the grapes that really have a preserving function and help to prevent heart attacks. Means plaque formation, etc. So a good glass of wine is good. I said the killer number 1 is cardiovascular disease. I think the killer number 6 is liver failure. So as I always say, I learned that here in the radio always, drink responsibly. Is that what you say? So the other one is we talk about also have that you get some exercise, and they are also saying have some exercise, but watch out, be also careful with that, not too much, because most of the time patients getting a little older, and if you can do that, okay, fine. But again, responsibly. So, and in case of any emergency, if there is any problem that you have, we can always say biomedical engineering may save your life. With that, thank you very much for your attention.
Obviously, these events couldn't happen without the support of our partners, very generous support of our partners, so we thank them for making these events possible. So join me again in thanking Professor Steinseifer for his presentation. Thank you very much. Thank you and good evening.